everyone to the epic meeting on microwave photonics with the entire value chain here in front of us. And the idea today is to continue with this amazing experience, which is to show everyone how good I look in underpants. So that's what I want to do with this meeting, to show you that I have also an electric guitar and I have mugs from all the different epic members. So VLC Photonics gave me this one. So you have presents for me. I live in Northwijk and you can find my post address at the website of Epic. So today is the 6th Epic online technology meeting. So far it's been a very successful experience. I would like to thank all of you today at the meeting and also the people in YouTube. Hello everyone in YouTube that are sending such a fantastic amount of positive feedback. This positive feedback is for giving Anna and me all the energies to keep going. So basically what we have to do is to just keep you happy. So we have now 500 companies behind us, 550 actually, we keep growing, 550 companies behind us, and you guys really want us to keep finding potential suppliers, customers, and partners for all of you. So that's why Epic has now 13 employees, 7 people with PhDs. We all try our best to understand what you do, although with companies such as, for example, Martijn, it's very complicated to know exactly what he does because he does so many things, and he will tell us a little bit of what he does later. So what I want to remind you before we go to the people who actually matter is that Epic is, on one hand, organizing a long set of present technology meetings. And when the situation normalizes, let's be very positive, in few weeks, when the situation normalizes, we have really, really cool meetings coming up. For example, we have the Epic World Quantum Technology Summit, which is happening next September in Glasgow. And I hope to see some of my quantum community there to find out what kind of business opportunities we can identify in quantum. And in addition to the meetings, we also provide our members with market reports. And I would like to highlight this market report that we acquired a few months ago on the indium phosphide wafer market. And the reason why I want to highlight this market report is because for today, it's actually very relevant. For those of you who had a look at it, it actually had a map of the different market segments and end users in the microwave photonics and terahertz market fields. In this slide is one from a case study of north of Grumman, and they actually mapped the 100 gigahertz all the way to the millimeter wave and sub-terahertz carriers and what kind of applications they are targeting. So it is actually very relevant. And one more thing to highlight, we have built the biggest photonics marketplace for jobs. Today we have already jobsinphotonics.com. So for those of you in YouTube who are looking for a job in photonics, do not hesitate to go to this website. We have looked at all the open vacancies of these 500 companies that they have behind me. We have put them in a website and we are willing to make sure that they get filled by the top talent that is watching us today in YouTube. And with this, I'm going to leave the floor to the people that matter. And the first person that matters here is Dr. Ana Gonzalez, who's going to tell us what is in the menu today. So what are we going to eat, Ana?
Thank you very much, Jose. So yes, I'm so happy to be here with this amazing list of companies. So as you know, to maximize the business generated at this meeting, we have an entire representation of the supply chain, focusing on end users. These are the ones who are going to tell us what they need, what are the challenges that they need to cover. So we have end users from the different, from the main application fields for microwave photonics, for telecommunications, broadband, wireless, and also radar, such as AIRBUS and Antwerp space. So also to help me with to explain you what are the different groups of the supply chain, I have this small diagram here, bottom right, that is representing the working principle for or how a device for microwave photonics works. So for this, we have usually an ARF input signal that is modulating through an electro-optical modulator, a laser. So when we have the information in the laser, we can perform different optical processing or functions. And then through a photoreceiver, we send the information out through an antenna, for example. So for developing, for helping our end users to develop this device, we have companies that are developing microwave photonic modules, such as iPRONICS, that is developing a programmable module based on photonic integrated circuits. We have the different foundries, because depending on the technology that you are using for the photonic integrated circuit, you can integrate one or more functions inside in a single chip. So for that, we have indium phosphide foundries such as TU Eindhoven, silicon nitride foundries such as LIGENTEC, and also a representation of JPIC spine online for ramping up volumes in indium phosphide, but also we need the packaging. So for that, we have packaging companies such as CSEM, also the PIXAP spine online for ramping up volume in your packages, and also Icon Photonics. Also companies representing components such as Lumiver and other organizations that are fabless. So they are going to find this very interesting because there are a lot of suppliers here, and we also are very interested of what can they offer as a technology transfer, right? So yes, this is all what I had to say. Did I forget something, Jose?
No, you didn't. It's great. We had the end users from the wireless broadband world. We had the end users from the radar, from the sensors. Let's try to understand what they need, and let's try what we can help them. Just a quick reminder from all those YouTubers, if you want to contact any of the participants at the meeting today, send me an email, jose.pozo@epic-asoft.com. My job is to connect you with them. So you are not asking any favors, you're asking me just to do my job. Send me an email, I'll be happy to make sure that you are contacted. And I ask all the participants in the meeting today that when I ask you to contact any of these people, please follow up to the best that you can. Our job really is to make sure that the industry is connected. And with this, let's now have a fantastic meeting, and we start with our end users today. I would like to give the floor to the first speaker today, who is Hakimeh Mohammadhosseini from Antwerp, Space in Belgium. Thank you very much for being with us today. Tell us how the space market looks for microwave photonics, Hakimeh.
Okay, good afternoon, everyone, and thank you, Jose, for your kind introduction. I'm trying to share my screen with you. Is it okay now?
It is fantastic.
Okay, perfect. Yes?
Go full screen and you're ready to rock.
Okay, thank you. So today I'm going to discuss with you Antwerp space activities in the field of space communication and also microwave photonics. So Antwerp space roots get back to 1962, where we were part of Alcatel Bell Labs.
Sorry, Hakimeh, could you go full screen? Could you go at the bottom on the screen? It's perfect. The floor is yours.
That's fine now?
No, not now. So it was okay for 1 second and it went back bad. So you go to slide mode. Yes. No. Fantastic. I think you are sharing the wrong screen. You are sharing the screen that is in front of you. You should share the big screen. So when you're clicking share.
Yeah, but I have two screens. So
yes.
If I make a bigger screen,
the beauty of this wall. I'm going to stop sharing your screen. Yeah. And then you're going to click share screen. And then when they tell you, they will tell you to choose which screen you want to share the one that has the biggest pictures. Yes.
Any change now?
Okay, I think it's the same, but we are going to continue. Just go ahead.
But I can do something else. I can disconnect my screen. And what about now?
Fantastic, you did it. Great.
Okay.
The floor is yours.
Okay, so I'm going to tell you about Antwerp space activities in the field of space communication and also microwave photonics. Our roots get back to 1962, where we were part of Alcatel Bell Labs. In 2010, we joined the OHB group, which is located in Bremen in Germany. And in 2015, we have started our photonic activities. So I'm going to share with you recent achievements of Antwerp space in the field of space communication. So we generally focus on design, integrate and deliver satellite communication subsystem for ESA science and exploration missions. For example, JUICE communication subsystem or Jupiter icy moon explorer, which is the first European mission to explore Jupiter and its icy moons. You can see here. And here, bottom corner, you can see a LARA instrument, which is actually a very compact radio science coherent transponder instrument. It is a transponder electronic box with 3 TX and RX antenna, which will communicate with Earth in 7 and 8 gigahertz ranges to actually measure how Mars rotates and orients. Also very recently, Argo modem in February 2020 has been launched and flight to International Space Station. So it will triple the download capacity of ISS. But these are all examples for microwave electronic domain, and the reason why we go for photonics, actually the rationale comes from JUICE communication subsystem. In such subsystem, there are a lot of bands, waveguides, and it is like a lot of mass here. So it makes a lot of sense to make use of microwave photonic capabilities to make such communication subsystem with a much lower weight. To give some numbers here, so if you want to transport 1 kilogram of mass to for example, Jupiter, it will cost 30 million euros, but to Moon, it will cost only 1 million euro. So it makes a lot of sense to reduce cost and mass for such deep space missions here. This introduction brings us here that what are our photonic activities now and in future in Antwerp space. Like dividing it to 4 divisions, we will develop the core element of laser communication terminals, the core elements of flexible telecom payloads. For example, you can see the frequency generation unit here, the frequency conversion unit here, switching matrices, and also in the field of radar instrument for front ends. So because this meeting is about microwave photonics, so I focus here on 2 of our activities in the field of integrated microwave photonics. So we have 2 main projects in this field, EPFC or electrophotonic frequency conversion, which is a project funded by ESA. It is a 3-year project with TRL level of 5 to 6. Here you will have a 50 gigahertz signal coming from the satellite, a low signal 30 gigahertz, and using photonic integration technology here, you will have 17 to 20 gigahertz K-band down converted signal. So in the center, it is very compact photonic chips inside the hermetic package. Around that, you have the control electronics, and then also we put RF front ends inside the package for this down conversion functionality. And here is the schematic, which shows very simple what happens. You have a continuous wave laser integrated with Mach-Zehnder modulator. And if you put RF and LO signals on top and bottom arms of the Mach-Zehnder and detect it at the photodiode, you will have the down converted signal. In our other project, Space Beam, together with our partner, we develop a photonic beamformer for radar receiver applications. So it is a project funded by EU and with 3-year duration and the same TRL level as EPFC. We have 12 antenna elements here, and here you can see the photonic integrated circuits, RF front end, and at the end we will have 3 down converted and beamformed signals. I come to the most important questions in this meeting, what we can do for you and what you can do for us. So Antwerp Space can be considered as an end user requirement provider, meaning that we can provide the requirements for your PICs for space applications. We also do as an end user equipment integrator, and we also can design integrated microwave photonic links for a space application, and we have heritage in control electronics and RF front-end design. And we always look for very important end users like satellite and payload integrators in the space sector, for the targeted application. And also we look for a space qualified components and procedure, either it is for photonic building block, for high speed and low power RF front ends, for packaging, and also for photonics and RF interconnects. And by this, I would like to thank you, and please ask me if there are any questions. And here you can contact either me or our business development manager at Antwerp Space if you have any questions. Thank you.
Thank you very much, Hakimeh, for a fantastic presentation. Especially you got the epic spirit by now. What can you do for them? What can they do for you?
Yes.
One of the key challenges was on the packaging side. What would be the ideal profile of a packaging partner? Because I have a few of them talking to me in YouTube right now.
Mm-hmm.
What would you demand from a packaging partner? What kind of packaging challenges do you have?
Yeah, there are different packaging challenges. One of these are like hermetic packages we always require, and also to consider the compactness of the final device. We always need to put like RF front ends inside the package. And then like, as I mentioned, a space qualified processes, if you want to do interconnects, either optically or electrically. For both, you need some interconnects that maybe are functional, for example, for polymers, but there we don't know whether they are, we need to make sure whether they are space qualified or not, and they can withstand the like harsh environments of a space. So these are very much related. And also in terms of end users, for example, the frequency converter that we are developing, we would be very happy if from the end users, like for example, AIRBUS or similar companies, to have like feedback about what are their requirements for frequency converters in the satellite.
Any questions for Hakimeh? Yes, Steve from CSEM.
Yeah, I would have a question about the technology you use, the photonics technology you use in your frequency converter. Is it a PIX you designed on purpose, or do you use commercial components like standard Mach-Zehnder modulator?
It is a photonic integration technology, and like normal building blocks that we have in integrated photonics. But in terms of the exact technology, we actually work with all technology providers in Europe. It should be in Europe, and it should provide photonic integration. So,
any further questions? Yes, Bob from Entropics.
The question is around the PICs themselves and the technology, and how they survive the radiation hardening requirements. Mm-hmm. I think that's still a challenge for most of the PIC technology. Do you have any feedback on that?
Yeah, that's true. That so part of it can be considered as you could consider de-risking activities, for example, to make sure about different tests that could be done before the final development. So that's really required here, that partners that could do like this kind of tests as de-risking activities for either a building block like a Mach-Zehnder, like a photodiode, or a circuit itself. So that's, I come back to the last slide. We always look for partners that could do this kind of radiation, or could say about how they could survive harsh environment.
I have a couple of questions from the YouTube universe. The first one is coming from Tobias Muller. He's a personal friend, but also the CTO of LIGENTEC and business manager of Fraunhofer IPT. He's wondering about the tolerances for alignment and bonding. Just so you know, LIGENTEC is a company that does active alignment, automation for active alignment and packaging of components. So can you comment on that?
Yeah, it's always a challenge here for coupling. There are some packaging companies that would offer such tests. So they do fiber coupling and these tests to make sure that it's withstand. but we are in the phase of development of these frequency, for example, down converter and also a space beam. It's in the very beginning phase, so we are still not sure what are the exact results in that respect.
A very important topic on the assembly is actually the bonding process. So I would like to let you know that actually LIGENTEC has a space-qualified bonding process technology. So something for you to consider offline. I have another question from my very good friend, Andreas Umbach. Andreas is wondering, can you comment on the different materials for photonic integrated circuits in terms of space qualification? Silicon photonics, induced phosphide, gallium arsenide?
Yeah. So the something that I can share is that, for example, we know that for polymer and plasmonics, we don't know whether they can withstand radiation. But I think for indium phosphide photodetectors, there are some tests that they did successfully on indium phosphide and it passed. But for plasmonic and for polymers, we need more tests to make sure.
I have a lot of friends with me, but I have also new friends. Ahmad from OptiWave. How are you doing today? Let me unmute you.
Yes, I'm fine. How are you doing?
I'm doing fantastic, as you can see. I guess you have a question for Hakimeh.
Yeah, that's actually, I'm asking about simulation capabilities for your projects. Like, I mean, do you use commercial software or you build your own software? Because this is, I mean, OptiWave is a software company which is interested in this topic and supporting the industry in this field.
It depends actually on the kind of activity we are doing, because for all the projects we have our project partners. So it's something that also needs to be discussed with them. So sometimes there should be similar software to use for development of such building blocks. So it always also depends on the other partners. But normally, yeah, we use commercial softwares, yes.
Thank you very much once again, Hakimeh. It's great to have you as an end user at EPIC.
Thank you.
You have been, until now, the link to many integrated photonics companies at EPIC to the space. You are playing a fantastic role in this ecosystem. The meeting has gotten serious because Gunter Rukens from IMEC and Sontal Liu from UCSB have joined. Welcome to the meeting. We continue with the program. The second presentation is from my favorite end user, Kasia Chesh. Thank you very much for being with us this afternoon. The floor and the attention to AIRBUS is yours.
Thank you, Jose. A pleasure to be here. Thank you for inviting us. And right, let me share my screen. Right.
Such a beautiful horizon.
Do you see it? Oh, that means you do see it.
Yes, I do see it, but yes, I know I see it fantastically. The floor
All
is
right.
yours.
So my name is Kasia Balakier, and I work at AIRBUS in the UK, and I'm involved in the development and definition of future products and systems. And I must admit at the beginning that EPIC team gave me almost an impossible challenge of presenting a company like AIRBUS in one slide. So this is what I came up with. So AIRBUS is the largest aerospace company in Europe. We have three business pillars, which are the commercial airplanes, then space and defense and helicopters, and I'm based in space and defense, and particularly in space business. So this is just a sample of what we do in the area of space applications. We divide our activities in number of groups. So we look at the telecom, so telecom satellites, anything between 1 ton to 5 tons satellites. We look at constellations. We work with collaborators on ground segments. Then the ENS, so Earth observation, navigation and science. We look at orbital systems, so the space exploration, in-orbit services and human space flights. And I could probably go on like that for quite a while, but I think the main reason why what I would like to talk about today is about the satellite communication. So in the topic of satellite communication, we can develop, well, we do distinguish number of links for satellite communication. So we can consider the direct transmission from the satellite to the ground, multi-user relay, when for instance, the information is gathered by LEO satellite, transmitted to GEO, and then from GEO satellite to ground. The broadband feeder links is where the big amount of information is transmitted from the ground to the GEO satellites. The deep space transmission to ground and intersatellite links. And I appreciate this is very simple representation of the vast, big selection of links and systems that AIRBUS is developing and building. But I wanted to highlight one thing, that all of those links can be realized in RF or optical domain. So this is where also photonics will plays a very important role. And then all those systems and communication links are mission, or should I say orbit dependent. So they will have different capacity, different antennas, different transmit and receive power, which will define our receiver sensitivity, different modulation formats. And again, so there are many differences in the system itself, which then will be translated into specification for the equipment that we will require. So this was about differences. There are similarities as well. And in the similarities, all those systems share same challenges. So of course, the size, weight, and power consumption, the swap is the very important parameters for us. So we aim to reduce it as much as possible. And I think this is where photonics is going to play an important role. Maybe not in power, although, well, we will see still. The harsh environment, and this is where, of course, the systems are, well, the system sensitivity to temperature and radiation is very important. And they put it in the common challenges, but actually that is going to be orbit dependent as well. So that temperature variation or the effect or expected effects from radiation are going to change depending on whether it's a low orbit or a geostationary orbit. And then the very important aspect that I would like to highlight is the cost aspects, which in a way hope that we will have a challenge to perhaps discuss it today. So moving to microwave photonics. That's been already introduced, so thank you for that. So in a way, microwave photonics, well, we see microwave photonics as a great technology with a potential for satellite communication payloads, and it's where we would like to use the microwave photonic systems to basically detect, generate, manipulate, and distribute RF signal in while it is in optical domain. So I put here 3 examples of the satellites that AIRBUS built. And we can see those very big RF antennas, meaning that we still receive the signal in RF domain, but it's may be processed in optical domain inside the payload to be then transmitted back to ground in RF domain again. So I included a number of opportunities where I think, so the business model for space is changing. The company has different requirements as the product we developed are changing. So now we see demand for very high throughput satellites and low latency systems. And this is again a really big opportunity for photonics applications. We do have a need, or we develop more complex payloads. So it's not anymore the bent pipe, which we had before. The payloads nowadays have processors, active antennas, and we also think this is where photonics will be able to contribute to what we are developing, shall I say, in traditional for the traditional payloads. The increasing bandwidth and capacity, and of course we know that optical photonic technologies or solutions are very broadband, so that's another opportunity for photonics. The generation and use of higher frequencies. So the higher in frequency we go, the bigger advantage photonics can offer. So we are now considering Q and V, but we started discussions about W band as well, and terahertz regions are being mentioned as well. The use and development of tunable local oscillators, which with low phase noise. So microwave photonics is not only about manipulating RF signal, but we also can generate really good quality RF signal using heterodynamic techniques. And I listed a few other photonics subsystems, which I think will play the role in the future. So those would be the optical switches, the beam steering, beam forming, and a very efficient laser sources. So that's something that we would like to have, but probably like everyone else. And the microwave filters. And that would be all from me. So yeah, that's my thank you slide and my contact details. So if anyone has questions either now or later, please do not hesitate to contact me.
Okay, thank you very much, Kasia. Very interesting presentation. So there is any question for Kasia? Okay, Lumiber.
Yes. Hi. I just have a quick question about the last idea you shared about the efficiency of laser sources. So what are the parameters that are you looking for to be more efficient than the actual laser sources on the market today?
So basically the way we approach the problem is that we would like to have as much optical power as possible for a very low DC consumption. So if there is anything that can be done to improve that number, that's definitely welcome. Another thing is that in many systems that we considered for the moment, of course, laser need to be temperature stabilized because of the efficiency. Again, if there is anything we can implement in terms of the laser temperature control, that's another route to go forward.
Okay, and what types of laser sources are you talking about?
So we at the moment considered semiconductor lasers for very similar to what we would use for the terrestrial telecom applications, which have been qualified for space.
Okay, thank you.
Rabat, thank you very much for the question, because that helps me position Lumibird a little bit at this meeting. Can you tell us a little bit what is the role of Lumibird in this ecosystem, in the microwave photonics world?
So a small introduction about the company. So it's the fusion between two French companies. The first one is AIRBUS, who is specialized in fiber laser and fiber amplifiers. And the other company is also French, who is Quantel, and they specialized in solid state laser and diode lasers. So now today we have some, let's say, fiber amplifiers for the microwave photonics for some microwave photonic applications, and we are just here to see what the market, the new needs that the market have today, and to see if we can how we can follow it up.
Okay, thank you very much for this introduction.
I have one question. So
perfect.
So it's just a follow-up with the previous question. So because the space environment is totally different from the Earth, so what's the other requirement, like the liability for the for the semiconductor laser for KCL?
All right. You're asking about the reliability of the semiconductor lasers.
Yeah.
So at AIRBUS, we normally, in most of the cases, we purchase components which are already space qualified. So it's our suppliers who deal with qualification of the components. Just to answer your question, the way we use it is, for instance, for the geostationary mission, we expect the laser or components to operate, well, the lifetime of the geo is 15 years. Yeah, I don't know if that's what you're asking.
Okay, yeah. Thanks.
Songtao, maybe you can take this opportunity to introduce yourself and what UCSB is doing.
Yeah, hi. Nice to meet you all. Right now I'm a postdoc at UCSB. I mean, mainly doing the the semiconductor lasers on the modular lasers, narrow linewidth laser side. I'm in Professor John Bauer's group.
Okay, thank you very much for joining today. So, okay, we have a question, Kasia, for you from YouTube, also related with qualification in the space. What important measures we need to follow to avoid radiation or to reduce loss due to radiation while using it in space? This is all the way from India, from IIT Madras. Yes, from India.
Right. Well, while in space, there is not much we can really do about the radiation. It's in their environment when the radiation is present. So what we work on is the packaging. So we do package, or our suppliers package components in such a way to make it less affected by radiation. And there, of course, on some of the components, well, not only lasers, there is a certain or slightly different way of designing them to make them radiation hardened.
Okay, and we have a second question from YouTube. I don't know from whom, but the question is good. Is there any preference integration platform preferred for all the components for the space applications?
Right. So, well, that's a very good question, and I think there is many people wondering about that. And I think our position at the moment is that we haven't excluded any of the platforms. So in general, people do have preferences for, well, indium phosphide or silicon. This is for terrestrial application, very often driven by cost. However, and especially very important when we have volume, like in data centers. For space applications, we don't have such a volumes, well, in millions. We do expect to have bigger volume, but it's not a volume which will affect that much the price of the component. So we look at still all the platforms.
Okay, very interesting. And well, there are more questions among the attendees. Okay, we will come back to you later, Kasia, because we didn't talk about what is the preferred technology for AIRBUS, if silicon nitride, indium phosphide, or silicon, but we have these presentations next. But no, this question about packaging is very good to introduce the next speaker, Steve Lecomte from CSEM. Okay, yes. Okay, so if you can share your presentation.
Yes. Do you hear me?
Yes, very good.
Okay.
Okay, you can put the present. If you can.
Yeah.
Use it.
Is it good?
Yes, that is perfect.
Okay. Good. So I'm Steve Lecomte from the CSEM, and I'll speak about the microwave photonics, in particular integration and characterization work we did at CSEM. So I'm not actually too much involved in packaging. We are more involved in my group at the system level. but we also have colleagues at CSEM doing packaging. So if you need anything related to packaging, just let me know and I will give you the right contact. So CSEM is a Swiss research and technology organization, and our main mission is to transfer technology to industry. And to give you a flavor of what we are doing, I will then go to through a couple of examples, but in the group, in the time and frequency group, we have 3 main research and development axes, which are quantum sensors, so basically atomic clocks, atomic magnetometers or gyroscopes, lasers. We develop laser sources, stabilized lasers, and laser-based systems, as well as 3D imaging lidars for ground and space applications. So now let me go through the 4 examples. The first one is related to the generation of ultra-low phase noise microwave signals. So here we talk about carrier frequencies in the couple of gigahertz to tens of gigahertz range. And the basic concept is as sketched here. So we use a mod-lock laser as optical oscillator. We use mod-lock lasers because those lasers are the best oscillators physics can offer us, especially those that are based on diode pump solid state technology. And we shine this pulse train, which lies in the hundreds of megahertz to gigahertz range, onto a photodetector to convert the optical pulse train into an electrical signal. By doing this, we already get quite, record low phase noise far from carrier. And if you want to improve also the close to carrier phase noise, then you can stabilize the mod-lock laser here by stabilizing the carrier envelope offset frequency of the mod-lock laser, here called F0, and its repetition rate. And for stabilizing F0, you can use a photonics integrated circuit, a waveguide, for instance, made out of silicon nitride. Here we used a waveguide made by LIGENTEC to generate the octave spanning supercontinuum and detect F0 frequency. In this schematic, you see also that we have an interleaver here. The purpose of this interleaver is to increase the optical pulse train repetition rate in order to improve the microwave phase noise. On the right, you see a typical phase noise we measured at 9.6 gigahertz carrier frequency of a fully stabilized system. And I will not enter into the details of this phase noise, but for those used to look at phase noises, this is really amazingly low phase noise values here. And I forgot to mention that the high power photodetector was developed by AIRBUS Optoelectronics in Switzerland, together with the CSEM for the characterization of the photodiode. And we also together made some efforts towards space qualification. This project was financed by ESA. Another example is this fiber microresonator. So at CSEM, we work with microresonators in different platforms like silicon nitride, but we also developed this technology here, which is based on standard telecom technology. So basically, you take a standard ceramic ferrule used in any optical fiber patch cord. You have in the ferrule a standard telecom fiber like SMF28, and on the facets you deposit dielectric Bragg mirrors. These mirrors have really low losses, and the fiber itself also has low losses. So you end up with a very high Q resonator with a Q value in the orders of 100 millions. And with this resonator, you can do different things. You can use it as an optical filter. You just use you can filter through the different transmission lines of the Fabry-Perot resonators. You can use it as an optical frequency reference to stabilize a CW laser. You can even use it to generate solitons. We generated solitons with pulse duration in the range of 100 to 200 femtoseconds, and also nonlinear filtering to clean up optical phase noise or even microwave phase noise once you have a soliton circulating into the resonator. So you have here publications describing these things. And what is also key to this approach is that it's very cheap and very handy. I mean, in order to couple the light into the resonator, you just plug it, mate it to a standard telecom fiber with a standard mating sleeves, and that's it. Another example is this ultra broadband optical frequency comb, which is based on electro-optic modulation. This system was developed to calibrate spectrographs that are used to detect or to find exoplanets. And there you need a broadband optical frequency comb with a line spacing in the 10 to 20 gigahertz range. So to do this and to be sure that the optical frequency of each line of this comb is super stable and accurate over time, we use this approach where we have a CW laser and then modulators that are driven by a synthesizer that is itself referenced to an atomic clock. Then we generate here picosecond pulses, we amplify them, compress them down to 100 femtoseconds, do spectral broadening, and then we end up with a super broad optical spectrum. And then this light is fed to the spectrograph. Also, the CW laser frequency has to be controlled, and this is done with a self-referenced optical frequency comb, which allows to bridge the gap between microwave frequencies and optical frequencies. And the comb also is referenced to an atomic clock. So at the end, you have this super broadband comb with super accurate optical frequencies that are necessary to calibrate the spectrograph. And the last example is this integration of a miniature atomic clock. So here at CSEM, we developed the key building blocks of such a clock. And what I would like to emphasize is that we even developed an application-specific integrated circuits here, so an electronic circuit which generated the microwave, in that case, 3.4 gigahertz frequency that drives a VCSEL laser that is used to interrogate the atoms that are in the atomic vapor cell here. And this full system was designed, realized, and characterized at CSEM. So what we offer system design and integration, as well as system characterization. And what we are looking for are collaborations with industrial partners for technological transfer and product development, as well as collaboration with academic partners to push the edge of what's technically possible in this domain. In particular, we would like to move more and more to photonics integrated circuits. So with this, I'm ready for the discussion. Thank you.
Thank you very much, Steve. We've been talking with many of your colleagues at CSEM offline about the next push for CSEM to be a partner on the photonic integrated circuit side. My personal point of view is that for already quite many years at EPIC, you've been helping many of the companies validate their technology for harsh environments, especially for the space one. You have lots of contract with the European Space Agency. I'm based in Noordwijk, so I know very well what I'm talking about. I think that is the role that you have to play also in photonic integrated circuits, because as you have seen already in the first 49 minutes of the meeting, most of the questions are, we still don't know how we can actually make sure that our photonic integrated circuits work in these harsh environments. Are there any questions for Steve? Yes, Martijn.
Thank you. I have a question on you show various ways how to generate a comp or microwave signals. One is a mode-locked laser directly. One is with ring resonate with ring resonators is an option. One is an option where you use modulators to create a comp and then further spectrally broaden that. There's a lot of diversity in approaches here on how that is, in the community. What is the most promising approach and the most robust approach, in your opinion, especially with the eye of future miniaturization on a photonic integrated circuit?
Well, it depends what you are looking for, actually. If you are looking for the best performances ever in terms of phase noise, for instance, and the tunability of the carrier frequency is not a big deal, then the Modoc laser approach with a high power handling photo receiver is the best way to achieve something. Now, if you want to generate multi-channels with let's say 10 to 20 gigahertz channel spacing, then the modulation comb approach, this electro-optic modulation of a CW laser, is a really interesting approach. And actually, this approach could be integrated in a PIC, right? If you can integrate the PIC, the laser, the modulators, and so then you can do that. And this has been demonstrated actually by research groups.
Steve, let me introduce you to a friend of mine, Peter Kuhn from QPS Photonics. Thank you very much for being with us this afternoon.
Hi, welcome.
Could you tell us, this community, could you tell us what QPS does?
We are into fiber optics and laser remote monitoring. And some of the applications are really challenging. They like to, for example, locate partial discharge in like transmission lines, which can be exceedingly long. And we need a frequency cone that are multi-line. And of course, we understand that this is a challenge. And we would like to work with a partner progressively and test it. So we would not try to go to the moon in one step, but understand that like we can first prove the concept by having, for example, a 8 or 16 lines, and that we can test out, how it works, and then we will push the envelope together.
Peter, you have now the lucky opportunity to meet some of the best experts I know in frequency comb generators here. So you have Martijn from Aarhus, University of Eindhoven. You have José Capmany from Valencia. You have Guillermo Carpintero. You have Gunther Ruckens from IMEC. All these people really can talk to you. But the reason why I gave you the microphone is that I also saw that Steve presented this fibered micro resonator, which look really interesting from my point of view.
Actually, we are using that, but in the form of the fiber, and the resonator is made by a cavity, as I seen in the concept. But there is another dimension in this type of work. Is the spacing between the mirror can be adjusted, and the sensitivity will go astronomically, and this is something that we like to do it, combine like that structure with the gyro, and this is of interest because last week we have been in conversation with FPGS, with a femtosecond laser that can write rating at whatever point continuously. So this is an ideal platform for us. And the fact is, femtosecond creating mechanical grating make it immune to radio, interference, and then the space application will be a very good idea as well.
Peter, Steve, you need to talk offline about this because I think there's obviously lots of room for collaboration. Actually, CSEM also have been working on some gravitometers in other group in the CSEM. So I think there is obviously a clear partnership. Peter, you joined also the fiber sensor meeting and you're already following up with some of the companies like FPGS. You are an epic star. Thank you very much, Peter. We move on with the program. I have the honor, pleasure to introduce one of my best friends in the EPIC community, Jose Capmany, CEO of iPRONICS, and one of the best teachers of photonics in the world. And I say that because I know that. I've been on the other side learning from you, Jose. Thank you very much for being with us. How is everything in Valencia today? I think we have you muted. You need to unmute yourself we can hear you with your beautiful, beautiful green headphones. Yes.
Hello?
Yes.
Can you hear me now? Yeah, okay, fine. So yes, I'm fine. The weather is well, it's a little bit rainy. It's not the typical Valencian, but it's not the typical situation anywhere. So
who cares about the weather outside? We have such a great weather inside. I would like to tell us how you're going to revolutionize the world with iPRONICS. Thank you very much for being with us this afternoon. The floor and the attention of everyone here and in YouTube is yours.
Okay, I'm gonna see if I can share. I'm actually doing the share of, but I get the desktop, but let me see, because I don't, I'm opening now, but let me see if you can you see my presentation?
Fantastic, crystal clear, the floor is yours.
Oh, but this is not the one, sorry. Sorry. Oh my God, sorry.
There's no problem. In the meantime, while you open the presentation, I would like to let people know that one of the passions of EPIC is to help young startups like iPRONICS. And now the presentation is up there. The floor is yours.
Okay. So that's the problem when you have so many windows open. Okay. So this is the presentation for today. So thank you very much for letting me introduce this iPRONICS, and in particular the field programmable photonic gate arrays, and in particular to microwave photonics, that, as you know, has been my principal field of work for the last 20-25 years. So, I mean, actually, one of the reasons why we are developing this approach, which is based on programmable photonics, is because we are finding the need to provide some kind of very flexible, fast, and power efficient hardware that can interface optics and microwaves. And this is because there are a lot of emerging applications that are demanding an ever-increasing flexibility, bandwidth, reconfigurability, and in one word, agility. And you can think about anything that ranges from changing or tuning filters in high frequency for a 5G base station, or collecting signals from wireless sensors, even IoT devices, even autonomous driving, and any kind of sensors that require a wireless interface with a fiber or a photonic segment. So we think that integrated photonics is definitely a very attractive technology, but in particular programmable photonics, because we think that it blends the features that are required to meet these requirements. There's been a lot of activities, of course, in application specific, and there will still be going, of course. This is one of the key products and key developments in integrated optics for many applications, microwave photonics included. And we have been working for many years on that, but we wanted to pursue a different approach that is based on what in electronics is known as an FPGA. And I'm going to try to explain very simply what the concept is all about. Okay, so you have like an FPGA is shown there in this view graph. So you have, it's a little bit bulky here because this is like a picture where we show it in a board, in a development board configuration, but you can identify, of course, a lot of different items, like, for instance, sorry, I was trying to put the laser beam, but it doesn't work. Okay, anyway, we have an optical core, which is where the intelligence resides. And then we have some interfaces from outside, the outside world, which can be RF connectors for your RF applications, electronics control, and some interface for programming. And of course, the real value of one of the big assets of this project is what is inside here. And what we have inside here is a waveguide and a programmable waveguide mesh, which is a mesh of Mach-Zehnder interferometers and programmable phase shifters. And you can program them, and by doing that, you can establish different circuits, and reconfigure them, even more than one at the same time. So to manage that in a smart way, you don't not only need the nice interfaces with RF, with electronics, but you have also to be able to develop a very, very smart software that is able to optimize your photonic core to make it resilient from failures, to provide control from drifts, etc., etc., etc. So this is basically what the company is focused about. And of course, the product has a lot of applications, but today I'm just going to talk about RF photonics. One of the key points is once you have developed this hardware, you need to have a smart software, as I said before, to be able to program this core. The core is made of this waveguide mesh and also some high performance blocks that can be interchangeable depending on the application. Can run from spirals, from modulators, lasers, etc., AWGs that surround. This is very similar to a FPGA concept in electronics. And the software is in charge of optimizing the resources, providing interconnections, and even providing processing functions inside. Okay, so for that you need specific languages, and so there's a big amount of work on both the hardware and the software. And what we can gain here? What we can gain here is that with this single product, you can emulate all the very basic functionalities that you need in RF photonics, from true time delay lines, from optoelectronic oscillators, from up-down converters, from instantaneous frequency measurement systems, beamforming networks, wavelength to time mapping, arbitrary waveform generation, etc. So we are very excited about the capabilities of this product. And of course, we envisage a future of applications where we can embed this product into different systems, as you see here, ranging from transport systems to also to autonomous driving, personal communications, etc. This is where we envisage the placement of FPGA. So I hope I didn't take a lot of time. Sorry for being so fast in explaining. And of course, if you have any other question and you need more detailed information, feel free to contact us through via Epic. Thank you.
Okay, thank you very much, Jose. Super interesting. Well, it's a super interesting platform. So first of all, I would like to ask if anybody from the attendees has any question. Okay, Kasia, very good. Yes.
Right, actually I have two.
Hi.
So, hello. So the first one is how quickly can you switch from one setting to another?
Okay, well, that depends on the mechanisms that you have for phase shifting. Currently, our prototypes work on thermoptic effect, which is not very fast, depending, well, it is fast enough depending on for some applications, but if you want a very super fast switching, then this mechanism is not fast enough, at least in the current configurations. So there's a lot of research going on trying to do thermo-optic phase shifters that are faster. But if not, there's also the possibility to resorting to a faster design for phase shifters. We don't work with those so far, but those based on current injection or current extraction on PN junctions can be fast enough, although they are lossy. Okay.
So do I understand correctly? And actually, that was my second question: that the software, the control of the circuit, the PIC, can be transferred from one PIC technology to another.
Oh yes, certainly yes.
Perfect.
Yes, because it's an object-oriented software, so it's more or less transparent to technology. The basic building blocks are based on objects.
Okay, thank you.
You're welcome.
Okay, Kasia, so I think AIRBUS can be interested in this new platform from iPRONICS. Very good,
Okay.
very good, very good. Okay, so any more question? Okay, Bob.
Question is related to the optics. What's the I/O count optically on this device?
I/O, you mean I/O input-output ports?
Yes, I do, yeah.
Okay, the ones that we are going to prototype now is 64 by 64.
Wow. And is there any wavelength sensitivity in the device?
Yes, of course, because we make it on silicon and we depend on the wavelength dependence of the grating couplers. But of course, we can design products to be operational on different wavelength ranges.
Okay. And what is the pitching of the optical input and output?
You mean the distance between the input and output ports? I don't know. I cannot give you this figure now because I'm not in charge of packaging, but there's somebody. But this is what we are targeting. Our first prototype targeted like 16 by 16, but we aim at 64 by 64. This is what I can tell you right now.
That's a lot of fun.
Project, yeah, it is, yeah, it is, yeah.
Thank you.
You're welcome.
Okay, great. More questions? Okay, because if not, we have questions in the YouTube channel. Okay, representation. What kind of optimization algorithms are you exploring for this optical FPGA implementation? Are you looking to machine learning, deep learning?
I lost the connection.
Okay, I will repeat, don't worry. Okay, so Jose Carlos Perez Romero from, I don't know from what company, says, great presentation. I have a question. What kind of optimization algorithms are you exploring for this optical FPGA implementation? Are you looking into machine learning?
Yes, we are. We do. Yes, we are looking for that. And we are developing algorithms that are based on cost functions. And
we just lost you, Jose.
This is one of the coolest things that has happened in the photonics community, having Jose Capmany developing an optical FPGA, who has been the dream of myself, and I actually have been discussing this with Gunther in the past, and we tried, and everybody has tried. It's doing something like, we have so many different questions to ask Jose when it comes to the crosstalk, when it comes to the packaging solutions, when it comes to how many units, how many cells we can do, even when it comes to the applications, deep learning, even when it comes to the algorithms. I think Jose has a lot to collaborate on this, and he already told us that he's looking for 3 types of partners. He's looking for a packaging partner. So for those in YouTube who can do packaging with ultra low losses and very efficient fiber to chip, this is the person to go. He's looking for companies who can actually help him with the slow insertion losses. Jose, no, you're back. I was actually summarizing that iPRONICS is one of the coolest things that I've seen in the last years. When it comes to deep learning, the deep learning application, what do you think is the added value of an optical FPGA? I think we have Valencia Internet already giving us. Jose, are you there?
Yes. Yes, I have some problems. I don't know why.
But no, but you're here. So everybody's
Yeah.
wondering about deep learning. This is the deep learning era. When it comes to deep learning, when it comes to the coolest application of an optical FPGA, what kind of added value do you see for an optical FPGA in deep learning?
Well, in this case, for example, it helps us to optimize the circuit, and that means to make the best uses of the resources that are available, but also to identify, we use the techniques also to optimize in terms of, hello?
Yes,
Hi?
yes. Yeah, yeah.
Hello. Sorry. Also to optimize in terms of different cost functions, whether we want to optimize connections or we want to optimize the number of hops, the number of phase shifters that we want to cross when we emulate a given circuit. Where is the best place to place the circuit given the constraints of already the circuits that are already being set within the available real estate. But the optimization here is a little bit integral approach in the sense that we try to tackle all the different aspects at the same time instead of going one by one.
Your optical FPGA always raises so much interest. My friend Mateo Cherchi, ciao Mateo. Mateo is wondering from VTT. Mateo is wondering about the power consumption of thermo-optic actuators. Have you have some power consumption back of the envelope calculation feasibility study? Something that you can tell Mateo so he's happy, because that's a very difficult question.
Yeah, we have them, but this nowadays they are not very power efficient, of course. But this is something that might be improved with the technology, with the evolving technology, or may force us to go to a different approach. Let's say, a kind of non-volatile approaches. So, yeah, at this time, we are aiming around 40 to 50 milliwatts per pi shift, so which is a lot, still a lot. So, but we'll see. We'll see. This is one of the things that we have to address. One of the challenges, because one of the things that has to do programmable photonics is to scale up. I mean, has to have the capability of growing up in terms of complexity and a number of elements.
Okay, and regarding scaling up, what are the challenges when talking about the packaging of your device?
That's a very good question. Yeah, the challenges are all. You have challenges everywhere. It depends very much on whether you have RF or you don't have RF. For example, if you have RF, then the scaling is complicated, because if you see like an integrated photonic circuit that serves an RF part, then you look at the circuit and probably 80 or 85% of the footprint is RF, and there's very, very small part is just the photonics part. But there are many things, like it has been said before, if you want to increase the number of input and outputs, then you need to have a lot of fibers. You need to have a very tight spacing between the inputs. Then, of course, if you want to scale up the elements, then you need to have more electronic connections, because you have to control your phase shifters, and then you can no longer go to wire bonding. You have to go to more elaborate electrical connection techniques, and maybe with different layers. Okay, so the more elements you have, the more complicated. You have to avoid crossings, etc. So yeah, there are a lot of interesting and exciting challenges there. Yeah.
Okay, well, regarding packaging, just to tell you that we have now the PixUp pilot line that is working.
Yes.
Assembly to go to large volume. So maybe we can talk later about if we can help you with the packaging.
Okay. Yes. Yes,
okay.
Of course. Looking forward.
Yes, sure. So then, and then regarding the photonic integrated circuit that you are using, what did you tell us? What material are you using? If silicon nitride, indium phosphide?
We've been using silicon, but silicon insulator, but this doesn't mean that it can be made on a silicon nitride, of course. Maybe, yeah, it's quite agnostic and technology agnostic. So it can be made in different technologies. Even you can use, probably why not in the future, transfer printing for integrating amplifiers to compensate losses, etc. So it's quite exciting.
Very interesting, Jose. Okay, so if there are no more questions.
No more questions, only that Icon Photonics wants to help you packaging pixels. They say that they want to help you on that. Icon Photonics from Portugal. Ciao, Carlos. And also
hello.
LIGENTEC also wants to help you as well with the packaging. Tobias Muller as well.
Okay.
So, yeah, so you are getting a lot of partners thanks to this meeting.
Thank you. Thank you, guys.
Okay, and then if there are no more questions or comments, I will introduce the next speaker. It's Michael from LIGENTEC, our silicon nitride foundry. So Michael, if you want, the screen and the floor is yours. Okay, Michael, maybe you have to unmute yourself, but we can see your screen.
Okay.
And now we can hear you. Very good.
Perfect. Thanks for organizing this this webinar. And in microwave photonics, this field is probably already it's quite some time that this field exists. And now the exciting thing is that photonic integration is getting mature to have a look at it, to have building blocks for microwave photonics also in integrated photonics. LIGENTEC is a chip manufacturing provider where we work in an ecosystem to develop the technology, fabricate the chips, and deliver the dies to the customer, and that is possible from prototype to volume. In the end, the chips will go in volume in modules or systems at the end customer side, and we work very closely with software houses and design houses like VLC Photonics in Spain. And here I took a picture from an article that actually David Martijn together with Jose Capmany wrote, where microwave photonics could be interesting, and especially integrated microwave photonics, because we want to go down in size and power consumption. And the needs are, I took only 4 here. It's high performance filter, low noise microwave generation, optical modulation, and high dynamic range. And I want to tell a bit what silicon nitride can do there, and what we can offer. And here's I want to start this the first slide with a slide that really shows the link between photonics and microwave to produce low noise microwaves with an optical signal, and that was done in a project together with CSEM, with Steve Lecomte in the Châtel, and EPFL with Tobias Kippenberg's group at EPFL. So we can take, for example, a CW laser, combine that with a very high Q cavity, and this we are able to fabricate, and then you can generate here a so-called frequency comb, what Steve already talked about, and this, when you put that then back to a photodetector, you get a very pure RF signal. And ideally, this RF signal is very pure. And how do we get a very pure RF signal? When the phase noise here, when the phase is locked in this frequency comp, and this we can achieve to a so-called soliton regime, where you tune this CW laser into this high cavity and then get a frequency soliton out of that. And that shows really the two links, where on the left side we are in the photonics world at 200 terahertz, and on the right side we are down to a few tens to hundreds of gigahertz, and that's the link that we actually make in this microwave photonics. Then we have obviously a few components that are important. That one was mentioned just by Jose. We have thermal tuning elements, and these tuners can be very efficient for silicon nitride, because our silicon nitride is very thick. The mode is entirely confined in the waveguide, and this is why you can bring the heater material very close to it. Also, we have developed the heater material where you can tune a resonance up to 4 nanometers, which is quite a lot in silicon nitride. Other components that we can deliver is true time delays or time delay interferometers, where we have where we get very low loss spirals, for example, or Mach-Zehnders in our platform. And here we can get a meter of delay in silicon nitride on a 5x5 millimeter chip, for example. But we are also aware that silicon nitride is a passive platform, and we need to integrate the best of all worlds together. And here silicon nitride is actually a nice interposer platform, and a nice platform where you couple the active elements very efficiently with good performances. Here, for example, coupling of a laser to a silicon nitride module, where we adjust the mode field diameter. We can do bonding, and here one example of a bonded 3-5 die, where we did high-speed photodetectors together with a research group in UVA with Andreas Bailing. And with this, I come to the end. We can show that photonic integration has a huge potential in terms of size, weight, power, robustness, and cost, where we can integrate optical components to a very small footprint, and we deliver the building blocks and the PICs for that. We have the basics with the high confinement silicon nitride waveguides. We can integrate actives, and we have a full creativity suite where you can choose all kinds of passive components. This, I would like to thank Jose, Ana, and EPIC to organize this event.
Muchas gracias. Thank you very much, Michael. So this is an EPIC event. It's an EPIC event. You're an EPIC VIP. Wherever EPIC goes, you go. So you know how it works. What can you do for them? What can they do for you?
It's mostly the value chain. So we know we can do fabrication of silicon nitride PICs, but packaging, system integration, getting the system requirements for all the building blocks I mentioned, that is something we discussing with some of the people here in this seminar, but this is where we never have enough offers to integrate our circuits.
Any questions for Michael? Yes, Rabat.
I think Bob was raised his hand before.
I think it's okay. Bob understands that Rabat first.
Okay, no problem. Thank you. In your presentation, you mentioned the basic component to generate the RF signal, which is a CW laser. Could you say a few words about this this source?
So that's the component is actually the key component is the high Q resonator, where you have a Chi3 nonlinearity, and so you tune a laser into this high Q resonator to benefit of the Chi3 performances to get frequency conversion in this high Q resonator.
Okay, and the laser source should have a narrow line width, or
the laser source needs a narrow line width, and it has to be tunable to a certain range.
Okay. Okay.
Bob.
Okay, questions around the waveguide technology. How easy is it with the silicon nitride to make a spot size converter for single mode fiber when you've got a laser at the other end that's nothing like that spot size?
We have done that, so that is I wouldn't call it easy, but it's feasible.
Okay.
But, this is something we have shown.
Okay, and what's the typical waveguide losses?
Waveguide losses is around 0.1 dB per centimeter.
Okay, thank you.
We have from Denmark, Hitesh Sahu. Thank you very much for being here today all the way from Copenhagen. So what do you think about this meeting so far, and what was your interest in microwave photonics, Hitesh?
Thank you. So I'm a postdoc researcher at DTU Denmark. So I'm primarily starting a new research direction, and that's why I'm here. So my research interest right now is using simulated Brillouin scattering, and as you know, it has recently generated some interest to use SPS to create microwave signals. And that's why I wanted to see.
How do you want to generate the Brillouin scattering? How are you going to generate it? How do you want to generate it? Is it on
so we're using Brillouin scattering. So you basically pump in a very high power light, and then you get reflection with a very narrow line width, which is shifted from the original wavelength by 10 gigahertz or something, depending on the material. Our main focus is basically to improve the material system. And we are looking into a novel like AlGas platform or amorphous silicon platform, and so hoping to create some nice microwave signal generators.
When I ask questions, normally I know the answer, so don't be afraid of that. LIGENTEC platform is very suitable for high power. Is that correct, Michael?
Yes. So we have tested up to several watts of power, and the power you can put into there is most the cases we have seen is that the packaging is the issue, and not the nitride platform.
I do believe here that there is a very clear wing-to-wing collaboration between the two of you. So I would say, we're gonna do our best here in these events, but after the event, the ball is in your court. So do follow up, especially the two of you. Any further question for Michael? Michael, have you been already active in space-related activities? How does the silicon nitride interact in this harsh environment?
So actually, the work I showed from this RF generation, this was an ESA-funded project, and before that, we have done studies to study of silicon nitride, and the optical effects were proven to be space hard.
Any further questions? I have a lot of people in YouTube asking different things, so I will actually let you know afterwards, but I have something for Steve. Another company from Switzerland, Menir Photonics, really want to offer you a mode lock laser with ultra low noise properties. companies. So they are going to follow up with you on that. I think there's also a clear partnership here. Michael, thank you very much once again for a great presentation. You will do a fantastic job. And thank you for keeping the manufacturing of photonic integrated circuits in Europe. It is great the work that LIGENTEC is doing as a silicon nitride pure play foundry. Let's move ahead with the program and let's give the floor to Martijn. How can I introduce you? Let's give the floor to Martijn. Thank you very much for being with us. Thank you all. The floor is yours.
I'm gonna.
Martijn and me are in the same country, in the beautiful Netherlands. And yeah, you click share screen, and you're ready to rock.
It's visible?
Perfect.
Okay. So yeah, thanks for the introduction. That is not really an introduction, but still thanks. I would like to present here on behalf of the YEPIX pilot line, which is the pilot line for indium phosphide-based photonic integrated circuits. I will introduce the pilot line a little bit, and secondly, I will then go a little bit more in details on what are the opportunities of such a pilot line for microwave photonics. So what is a pilot line? So first of all, we talk indium phosphide photonic integrated circuits. So very brief, of course, most of us are experts, they know it anyway. A photonic integrated circuit is where we bring together lasers, modulators, photodetectors, filters, waveguides on a single piece of indium phosphide on a single substrate to make a chip. Well, that is actually an old technology, right? It has been empowering our internet for our communications for over 2 decades. But the thing is that typically these kind of companies are quite vertically integrated, having their own manufacturing facilities, having their own processes, etc. That is, of course, a little bit, there's a large bottleneck if you go from other fields going into this field, for example, from the microwave photonics field. So a decade ago, this was sort of tackled, you know, bringing this technology to the market in applications outside of telecom. So a decade ago, this was tackled by the introduction of things like multi-project wafer runs, sharing a production facility, a manufacturing facility, sharing a common process, basically building on a common set of building blocks. This technology became accessible for a lot of other markets, including microwave photonics. However, that was more or less at TRL levels of 4, so prototyping, proof of principle of your idea. From that point, all the way to actual sales, production, commercialization, turned out to be quite a big step. And here come in the pilot lines. And in this specific case, actually, there are many pilot lines. This particular one is for indium phosphide. So what does the pilot line do? You basically scale up your prototype through mature foundries. In our case, that is Smart Photonics in the Netherlands, Heinrich Hertz Institute in Germany, and 3-5 Labs in France. So we scale up to TRL 7, which we basically call a pre-production level. Practically, that means you go from a handful of devices to tens or a few hundreds of devices, and everything becomes far more robust. So this pilot line was kicked off a year ago. So we are now getting into the flow, into manufacturing. So in a nutshell, a little bit, what is enabling the pilot line? That is a manufacturing grade process design kit. What does that mean? That means that due to a far larger volume of wafers in the fab, far more testing, we get far tighter margins on the process variations and on the description of our devices. That means that with our software partners, if you make a process design kit, it's more what you expect to get, what you design is what you actually get. So those tolerances, those robustness, it becomes far more tight. The capacity will be increased a lot from prototype level to pre-production level, tens of wafers, in single-digit wafers to tens of wafers. The pilot line is now being, we are in the process of validating it for 2 specific businesses, communications with Mellanox and fiber sensing with Technobis, to show that it actually works. But that does not mean that it's not open for other users. So basically our offering here is that within a year or so, we will open the pilot line for anyone who's interested at cost level, although we do have some support if people are interested. The pilot line, although it's funded by the European Committee, the Horizon 2020, it's not a project. It's supposed to be an entity that is sustainable beyond the project. It's there to stay in the ecosystem. I think that's very important to mention here. And finally, within the pilot line, if people are in need of some support, we have the expertise to actually guide people through this whole system. So that's the pilot line for photonic integration on indium phosphide. That's very generic. There are a lot of different applications possible. Now, specifically for microwave photonics, why is this interesting for microwave photonics? Well, microwave photonics, especially if we look at the higher end microwave photonics, what we need is high bandwidth, obviously, because we need the microwaves, the millimeter waves. We need high power handling for large dynamic range. And we need ultra low loss performance for example, filtering and delay lines. Well, if we look at microwave photonics, the high bandwidth, that's actually no issue. That is inherent to the indium phosphide platform. These foundries that we work with, they can do tens of gigahertz in the photodiodes, in the phase modulation, in the absorption modulation, and in direct modulation of lasers. So there's no issue there whatsoever. Basically, it's the best platform to do that. High power handling, that becomes a little bit more tricky. Yes, in indium phosphide, we can make high power lasers and high power photodiodes, but in these specific circuit platforms, PIC platforms that we are pitching here, that is not native. But that does not mean it's not possible. There are all kinds of tricks, optimization by circuit design, to actually make it high power capable. For example, you can parallelize a lot of photodiodes to boost the saturation power there. You can, of course, widen up lasers, amplifiers to boost the power there. So there's a lot you can do for microwave photonics with circuit design. And the final point, and actually that's very nicely synergetic to Michael in the previous speaker, ultra low loss is required. However, indium phosphide does not have ultra low loss, but for a lot of applications you really need it. And there we see a very nice match indeed with platforms like silicon nitride, which can actually achieve Q factors getting close to 100 million, down to 0.1 dB per meter, maybe if you stretch it. And that is enabled, this integration, by the fact that we do have spot size converters to make them nicely together, to hybridly combine them together. And of course, things like hybrid packaging are now getting quite mature, also on a commercial scale. So even though we talk about a platform for indium phosphide, there's also a pilot line for indium phosphide, there's also a pilot line for silicon nitride, and these go very nicely together when we talk about opportunities for microwave photonics. With that, I would like to end these 6 minutes. So, and here you see the partners that are available in the pilot line, all the way from the foundries, the software, the design houses, the software tools, and all kind of support services. So thank you for that.
Okay, thank you very much, Martijn. Great presentation, well, as always. So, okay, there are any questions from the audience to Martijn? Okay, if not, I have questions for you, Martijn. So, okay, what do you think about hybrid integration? What do you think that are the challenges to get them? Because it seems the perfect combination, right? You have low losses silicon nitride waveguides, and then you have the indium phosphide laser. So, what are the challenges for that?
The challenges are the obvious challenges first, actually doing the alignment in the packaging facility, but I do understand that there are facilities that actually optimize that actually dedicate themselves to that. I think a year ago, for example, LIGENTEC was giving even a course accessible to the whole community in in actually, you know, learning how to design for hybrid integration. So that is available. I'm not saying it's easy. I'm not the expert there, so I'm not sure whether someone from Lionics is actually in this call. But yeah, I saw Paul van Dijk, he's actually in YouTube, but okay. So that is maturing anyway, so that's possible. That is the obvious thing. Then one step back or to the more details, making the correct lengths and, you know, taking cleaving and dicing tolerances into account. That is for some applications maybe a little bit of a bottleneck, because that means your optical paths are not very well defined.
Okay, and I have a question for Hakimeh from Antwerp Space. Hakimeh, I know that you know Martijn very well, but did you know JPIC's pilot line before? And what do you think about indium phosphide for space applications?
Yeah, so of course, indium phosphide has a lot of functionalities to put all the functionalities we need on the chip. For me, was a question that what is the maximum laser power that could be achieved there or could be tolerated? What is the maximum high power laser with this platform?
So there are multiple. So if we look at a normal laser that you typically get as a basic building block, we typically talk about 20 milliwatt for these platforms. When we do tricks like tapered amplifiers, we can boost that with a certain factor. With some modest tapering, we already had 50 milliwatt as a first try. But on top of that, just like with photodiodes, you can do tricks like parallelization of amplifiers just to avoid the saturation that's happening there. So I would think with some tricks, I mean, we have already easily shown that you can go far beyond 50 milliwatts, so 50, 60, 70. But definitely getting into the 100 milliwatt regime should be possible there.
Yeah, okay.
But not the watt regime.
Yeah, thank you.
Okay, and then we have a question from Kasia, AIRBUS.
Unmute. Right, I just want to double check about the availability of building blocks through the pilot line when comparing to MPWs. And actually, why would we choose the pilot line and not, for instance, replicating our design on the MPW 100 times?
First, well, I think that's a good question because let's put it like this: the pilot line, the multi-project wafers are a service that is to a certain extent a reflection of the quality that we are now scaling up of the pilot line. So to a certain extent, these processes go hand in hand. It's very foreseeable that the multi-project wafer runs, the quality will go up as a result of the pilot line, the fact that the pilot line exists. Is in the end a matter of volume. So the multi-project wafer runs, they are of course limited to a few square millimeters. So they do allow you to play around. They definitely do allow you to play around and to, as a proof of principle, to figure out what you want. Can you do that? But what it does not allow you is to actually get also internally in your company to get enough volume to actually test the manufacturability of your device. Of course, you were saying the hypothetical case, if you do 100 runs on a multi-project wafer run, but that is inherently not possible in multi-project wafer runs because there's, by definition, a limited amount of wafers going there, unless you find 10 other partners that want to go for 100 runs with you, in which case that is possible, but that is not the definition of multi-project wafer run.
Okay, very good. I can see some interest here from our space companies. Very good. So then there is any other question for Martijn? No? Okay, so
also, I have also one more question. It was mentioned that you went for specific companies the first step to see how this works? Any reason for selecting those application and, for example, not a space application, how to say, or whether in future a space application could be considered in this pilot line?
Typically, validation partners are, so typically a pilot line is mostly useful for people, companies who already have some experience with the technology of photonic integrated circuits. So you can, I mean, very black and white, you can argue companies who have some experience going on multi-project wafer runs. So they know what to expect, and they know that it makes sense to start scaling up. Because if you start from zero, then it might be best to start with multi-project wafer runs anyway. So the pilot line is for scaling up, for dialing in your own manufacturability, and for actually, saying, we want to go to the market. So that is quite more mature, typically more mature players there. And a specific choice is, of course, because those are two very important markets that have the opportunity to go for high volume. Fiber optic sensing can be ubiquitous. I mean, communications, I don't even have to explain, but fiber optic sensing can go everywhere. The bottleneck at the moment is the readout unit. And if you can bring that on a chip, well, then it can literally virtually go everywhere, from bridges, infrastructure, to airplanes, to indeed the wings of the airplanes of AIRBUS, maybe, you never know. They might already be there actually. So so those are two very clear opportunities.
And also another question, is there time for it? Yeah. Okay, is there also control electronics and RF front end considered, or is just about the photonic technology itself?
That's a very good point. I think we are now mapping, well, especially EPIC is involved in that. We are mapping not only potential customers, but also potential, I think we call it beneficiaries, people, companies that make up the full ecosystem. I already gave an example that for microwave photonics applications, you want to combine indium phosphide with silicon nitride, for example. So that's, there's actually a pilot line for silicon nitride. So that needs to be combined. Then I don't even talk about packaging. There's a pilot line for packaging. We ensure that we keep compatibility with specific packaging templates so that all these pilot lines are ideally, seamlessly, they can go together. But then we only talk about the optics, the photonic module only. So we are indeed thinking about to which extent we should build relationships with people, companies who can figure out the drivers. It's of course another expertise. It's also expertise that the companies might want to have themselves. But it's a little bit an open-ended thing that we think about, but it's not the responsibility of the pilot line. I mean, what we do is make photonic integrated circuits, do it at high TRL levels, and do it as well as possible. That's the important part.
Mm-hmm. Okay, thank you.
So what is the entry cost like for individual user or academia user? Like $1,000 per millimeter square or something like that?
Okay, these prices are public. So so a pilot line is again high TRL level. So that is then you pay for the whole wafers. So that will be relatively expensive. But the step towards a pilot line run is typically a multi-project wafer run. And there you pay, I mean, you can look it up on internet, probably a few thousand, $5,000 for 4x4 millimeters, for example.
4x4, oh, that's nice.
With academic discount, sorry. But you're UCSB, right? So.
Sure, thanks.
Yeah. Martijn, my friend, I have a lot of interest here from YouTube. First one, Matteo Cecchi from Finland, the most beautiful Italian guy in the whole Finland. Is there any open access silicon nitride platform that really provides resonator with 80 million Q with no special process?
Well, so this is, of course, these numbers, they come from previous work that was done in the past by Lionics together with UCSB when I was still there. So that is open access in the sense that it's an open foundry, so you can go there for this technology. This is not, these loss numbers are not the multi-project wafer runs that are currently being offered. But that being said, if you want to have very low loss waveguides, that's only beneficial if you actually want to make very long delay line. So if you want to make a few tens of centimeters, then you don't care. If you want to make tens of meters, you care. And then it becomes so long that you need the whole wafer anyway. So
you're referring to this beautiful paper that with the 0.1 dB per meter losses in 2011, where LIGENTEC was also involved. I would like to say hello to my very friend Paul Van Dyke. I know he's watching us. You should be here with us, by the way. Michael from LIGENTEC, can you comment on that? Are there any way of getting these 80 million Q factor resonators?
Yes. What was shown by there's a few differences in platforms, and one is definitely the thickness of the nitride. And if you go very thin in nitride, then your mode is guided by the nitride, but the whole mode is mainly in the oxide. So you need very low loss oxides. That's the trick here to get this. And Martin knows that better than me probably, to get this very good Q factors. On the other hand, you can also engineer your silicon nitride waveguide in a way that your mode is entirely confined in the nitride, and then the advantage that you get is that your bend radius suddenly goes down from a few centimeters or millimeters down to a few microns, and so you save a lot of space on the wafer. And then doing that way, going with thick nitride and this low bending radius, then you can get Q factors. The best that was achieved in an R&D process is around 30 to 40 million. So I'm confident that this is also possible to get there with thick nitride. So nitride in general is a very good platform to get these very low losses.
I think that's a clear statement, also one of the conclusions of this meeting. It looks to me, when it comes to the platform of choice, we have here indium phosphide light sources, indium phosphide detectors, and we have silicon nitride low losses. I have a statement, Martijn, a statement from Eamon Murphy, our friend Eamon Murphy from the European Space Agency. He's helping EPIC a lot into mapping the needs of photonic integrated circuits for space. He's saying that the two of you are really already working a lot, talking a lot about the silicon nitride platform and the requirements for space technology. But on that line, our friend Amin from Antwerp Space is saying, do you have any update, Martijn, on the indium phosphide suitability for space applications?
Yeah, that's very hard because I was in the new space meeting that you organized as EPIC. And the main message was that, only the end product can be considered space qualified. So I won't be talking about space qualified because that would be too much. What I was already showing there, and what I can say and what might build some confidence, is that these kind of chips have been tested, for example, by Technobis for space applications. And that might be not your application, so that is their application. It might give some confidence that there was hardly any degradation in there was almost zero degradation in loss. There was maybe a small phase shift, and there was hardly any degradation in the emitter components, so in the transmitting components, the laser, the LED. So they are in the process of space qualifying it. They are basically shooting these chips into the air, right? So it works.
All the way from Rochester, University of Rochester, my very good friend Jose said, what is the bottleneck right now in scaling to higher volumes of indium phosphide?
The bottleneck in scaling. So there are a few bottlenecks that we address. One bottleneck is going to larger wafer size. That is ongoing in the context of this pilot line. So we go to the larger wafer sizes. of course, one of the bottlenecks when we talk indium phosphide versus silicon, and that is a very well-known issue, is that the silicon processors, they can benefit from the whole electronics infrastructure. So if you want to have really high volume, but we talk a million, we talk not 100,000 devices, no, we talk tens of millions devices, then you can really benefit from that. And that is under a million devices, then you cannot fully benefit from that anyway. And then you have a little bit more manual work, or you overpay, obviously. So the technology infrastructure is, of course, slightly less mature than the electronics industry. And very practically, the example is, of course, that the wafer is just more brittle and it breaks more easily, and many practical details there.
I want to just clarify here, when it comes to scaling up, right now foundries like Smart Photonics are already providing quite high volumes already for most of the applications. So there's only a few applications in terms of transceiver for data centers or in the sense of IoT or consumer electronics that are the challenge. But definitely for any application that is targeted by AIRBUS today, I think we are fine right now with the 3-inch, soon to be 4-inch wafers volume production by Smart Photonics. I would like to say hello to all my friends in Eindhoven. You're doing an amazing job with the indium phosphide ecosystem. Photon Delta, you rock. And we go back to Anna, who is going to introduce the last speaker today.
Yes, it's my pleasure to introduce Guillermo Carpintero from the UC3M. So Guillermo, if you want to share your screen.
Okay, first I will unmute myself.
Very good.
So you can hear me, okay. And okay, right now I will share my screen. Actually, okay.
Yes.
So, are you seeing it in full screen?
Yes, very good.
Okay. So first of all, thank you for inviting me to contribute in this session in microwave photonics. First, I just wanted to present you my group, and we are 2 full professors, and we are quite a unique group in our university. We are the only ones working in photonic integration, and actually our field is in microwave photonics. We have been working in this field since actually 2010, when we started a project, AIRBUS, on integrated photonic transceivers. Actually, the idea, you know that in a generation of microwaves, it has always been use 2 lasers in an optical heterodyning, so 2 lasers beating in a photodiode, and we actually thought about integrating this in a single chip. And this chip was fabricated during this project on 3-5 labs. That's why I decided to put the reference authored by Frederick. And he fabricated, we designed, and it was fabricated within the project, this chip, which to date probably includes all the functions that you need on a millimeter wave transmitter. Actually, these 2 lasers could separate wavelengths between 20 and 110 gigahertz, and included the optical combiner and different amplifying stages, modulators, and high-speed photodiodes. This was our first demonstration of a photonic integrated circuit to generate millimeter waves. And since that, in our group, and this is, I actually named these slides in the questions that I was asked to. So what we do, this is where we started what we are actually doing, and we have actually fabricated different chips. We moved more recently to chip that I just showed you, this was on, as I said, 3.5 lab foundry. And this was on a dedicated process run because involved 3 epitaxial overgrowths. And we actually demonstrated sometime later that this could be achieved in a multi-project wafer run in HHI. And this is also in indium phosphide. This is actually in the NWP run from JEPIX. We have not only this laser could tune their wavelengths. Actually, the initial spacing of the two lasers was 500 gigahertz, and we could tune them down to 0 and crossing wavelengths. So we could actually show that we had an optical source to generate any frequency from millimeter microwaves to terahertz. And actually, this configuration is the scheme was for a terahertz spectroscopic engine. And we have not just worked on optical heterodyne, we have also worked on pulse lasers. These are different types of mode lock lasers operating in 100 gigahertz in a multiple colliding regime, and actually down to 1 gigahertz. We are covering all the frequencies across these two with indium phosphide fully integrated mode lock lasers. Of course, the frequency that we get from mode lock lasers is fixed, and then we have actually very high quality, low phase noise, but fixed frequencies. And on the other side, with dual wavelength lasers, we initially thought that putting these lasers together in the same chip would remove the drift and the jitter from having two different thermal controlling stages. And still, what we found is that even when they are both on chip, we still have some noise issues and some drift between the two lasers. We are actually now working to address this. And one of the things that we have specialized, and this is what we offer, is that we have specialized on the design of these chips, but also in the interface with the antennas. Because actually, photonic devices have the unique feature of being broadband. You can, as I showed before, you can generate from 500 gigahertz down to 0. But then the problem is that it's so broadband that when you go into the electromagnetic side, then you hit the problem that electronics is not that broadband. And you have the problem to exploit the wide tuning of optics into the electronic domain. Because if you are fixed to the same wavelength tuning because of the size of the rectangular waveguides, probably you don't gain much advantage of having broad tuning in optics. And that's what we are now addressing. And what you can see here from photodiodes that were fabricated at 3.5 labs, we have integrated these modules. Actually, we got bars of photodiodes. We are integrating them on antenna arrays. You can actually see here a two-element array. You can actually see the size, and with absolute power measurement of electronic absolute power measurements, we have determined the power that we are radiating, and we have demonstrated that this is when we bias only a single diode, and this is the power that we are reaching with one element. This is consistent with what we had already measured in the project. And when we actually bias the two diodes simultaneously, we actually get a 3 dB increase in the emitted power. And this is one of the reasons why we want to go to optics, because actually you can, it's much easier to build antenna arrays, and actually you can use photonics to steer the beam. And we are actually achieving that with plus minus 10 degrees of steering with optical techniques. And that means that we don't have any power penalty in the steering. This is part of what we are doing, and it's related to the optics. And this is the part on the transmitter side. We are also working on the receiver side, and as you can see, we have developed Schottky biarray diode receivers that cover from 100 gigahertz to 300 gigahertz in RF carrier frequencies with 10 gigahertz of video bandwidth. And with this system, we have also been able to measure bit error rates of wireless data transmission, and actually demonstrated that if you can assume the fixed frequency of pulse lasers, you are more efficient, because you need less optical power to achieve error-free level in the bit error rate. And finally, what we look for we are a university, we look for challenges. And I just wanted to share with you the last challenge that we found. It's a Fed Open project. And as I said before, we are dealing with beam broadband, exploiting the advantage of the photonic potential to cover an extremely wide frequency range. And we are using this to actually, well, if you have done measurements in high frequency, you probably have a vector network analyzer. And these usually cover up to 70 gigahertz, the most expensive baseband systems. If you want to go beyond, you need usually extender heads. They cover up to 330 to right now. This was probably this is 1 year figure. From then they have now moved. They are reaching, trying to push this to 300. And the problem is that this is the highest frequency in coaxial. If you want to go even higher, you need extension heads that use rectangular waveguides. And the problem of rectangular waveguides is that then you are in a banded situation. You can only cover a certain range of frequencies and still be single mode. In this project, we are exploiting photonics to actually cover 2 decades of frequency in a single system. And okay, this is what I wanted to present, and thank you very much for this opportunity.
Thank you very much. Thank you, Guillermo, for a great presentation. Thank you, all of you, for a great discussion. Guillermo, you're looking always for partners, always. This is what I like the most about you. You always say, these are the people I really want to work with. Which kind of partners are you looking out of this meeting here and in the whole YouTube universe? What challenges, what partners are you looking for?
Actually, in this project, we have involved Fraunhofer HHI, because actually one of the things that we see now is that we are moving from monolithic integration to hybrid integration. One of the things that we learned is that monolithic it's too complex. And you gain a lot when you move to hybrid integration. So we are actually looking to alternative substrates, and any partner, any company that is doing other substrates from indium phosphide, we are looking at them, because actually for the electromagnetic side, indium phosphide is not very friendly, because actually absorbs the electromagnetic radiation, and then you get a problem when you want to go into an antenna array structure, because it's extremely difficult to extract the electromagnetic radiation from indium phosphide and still have an array beam. The other things, we are also in this project, we have Anritsu, and basically the DNA that you see in the slide is from Anritsu. And actually, the idea came from discussion that we had. They were showing us their VNAs, and we thought, okay, it's nice, but you know, it's extremely difficult. It's extremely expensive to go from to buy all the extension heads that you might need to go to 1 tera. It's actually 1 million euros to get all the extension heads that you need to cover the entire range. And
so you are too expensive for the community. And Ritsu, if you are listening to us, lower your price, or we are going to buy from somebody else who is member of EPIC. We have a few questions here who are, what is the largest antenna array you have driven with these PICs? This is from Rochester University.
Okay, thank you very much. It's in collaboration with signal theory department is the colleagues we work hand in hand with. They are also involved in this project. The largest array that we have been able not to fabricate, but to measure is 4x4. It's a self-complementary array antenna because when you put so many elements, it's a challenge to bias all the individual elements, that radiating elements that you put, all the photodiodes in the array. And we had to develop specific structures in which the antennas actually acted as bias access points to all the elements in the array.
Any final question for, yes, Martijn?
Yeah, actually, it's a little bit of a follow-up question to what the question that Hakimeh asked me about electronics. You know, whether we consider electronics. Of course, we know electronics designers are available in Europe, and we only have the question, should we relate to them? But I was triggered by what you said. You do a lot of this terahertz for the, well, sub-terahertz antenna work yourself. So, of course, we want to make a manufacturing ecosystem in Europe. I mean, we already have a lot of people, a lot of companies working on packaging, on the chips, on, and of course, we have electronics. But do we actually have in Europe players that can provide, let's say, packaging, including antennas in the 100 gigahertz range and up? And if so, should we maybe connect them to the ecosystem?
Yeah, we do. We do have a few antennas. Actually, we have even companies in Spain. There is the RF community is very rich and very strong in Europe. And in terms, actually, in terms of packaging, the companies that I know, the company I know is Anteral, and they are actually very comfortable with antennas, and they work in waveguide structures. That's the main feed for millimeter waves antennas is rectangular waveguides, and they have actually the company that we work with for SBDs, for the Schottky diodes, now they do their own packaging. So and I think it's the interface between the photonics and the rectangular waveguides where is missing link. And that's the link that we are trying to fill up right now, because actually our photodiodes have their own specific features, impedance, biasing, and when you need to couple this to antennas, actually when you work with the antennas as contacts and as access ports, it's really an advantage. And that's why I said we are moving also to hybrid, because when you change materials, you have even an advantage. And I think that hybrid integration has a huge advantage in millimeter wave photonics.
Bob, you have been working in indium phosphide for quite a certain time. Bob Musk from Entropics. what do you think has been the developments? What kind of things you have seen changing towards addressing the needs of microwave photonics within phosphate?
Interesting question. I think one of the issues comes up quite often is the fact that people talk about multi-project wafers, but what they forget is a multi-project wafer actually defines the structure of the product you can make. And as a classic example, a lot of the epi structures won't allow you to make spot size converters in them. And it's something that the industry needs to be made more aware of. It's not as simple as it seems with the multi-project wafers. And also, if you remember the project Paradigm that went through, that was trying to standardize also the design of the packaging. That unfortunately still hasn't happened. I know all the JAPICs, etc., are trying to do that, but standardization is the key in all of this, and it's still not been addressed in my mind.
We have now shared with all our members the design rules of PIXAP, but there is a long way to go for actually fully having a standard packaging, actually application-dependent standard packaging. I have questions from the two end users from Antwerp Space and AIRBUS. So first, Hakimeh.
Thank you. Just a question. Have you explored the possibility of a space application for any of your work?
The question is to Guillermo Carpintero.
Yes, we have, because we have a relation with a Spanish company. We have a relation with CENER, also with Alter Technology. And we are currently involved in a regional project that it's called Martin Lara. And this project is about developing millimeter wave radiometers. Actually, these are fixed frequency radiometers. And we are actually trying to measure millimeter wave radiation to detect the absorption of the atmosphere and detect the humidity. And these are for weather prediction. And it's based on a nonlinear resonator to upconvert the millimeter wave into the optics and do the processing in the optical domain. So it's actually about using photonics to process electronics. And the idea is to reduce this. The resonator is a few millimeters diameter. And the idea is that we can couple, we can generate all the optics to drive it with integrated photonics.
Yes,
what about the RF front end? Have you considered space qualified components for the RF front ends?
Actually, that's we can always we are relying in that there is a huge database of electronic components that have already been tested for space. And the problem that we get to is using photonic integrated circuits in space, because we know that there has been some test. I wouldn't say qualification, because I don't think they reached to that level. But there has been some tests on individual components, such as big cells, some DFB lasers, optical amplifiers, but as single elements, not as components in an indium phosphide wafer. And usually, that's always the first question that we get is, has this technology been qualified? And yeah, we are far from having anything done right now, but it's within our scope. And actually, one of the companies that we are in contact with, which is Alter Space, is specialized in space qualification. So I know they are interested in this, and we are trying to establish some collaboration to get at least some answers on this issue.
I would like to say hello to my friends from Alter Technology and OptoCap. I hope life is very good over there in Madrid and Glasgow. Kasia.
Right, so I have two comments actually. So one, to follow on what Guillermo said about the qualification and actually the whole discussion about qualification of photonic integrated circuits. So we shouldn't be really afraid of that, because we know that photonics has already a heritage in space. We have had photonics flying many years ago, and it survived quite actually beyond our expectations. The problem we are going to have is when we start to qualify, and this is as well in relation to what Bob said, when we look at the NPW's runs from two different foundries, we do receive very different performance and very different wafers. We cannot just assume that if one has been qualified, the other one is going to perform in exactly the same way. They are going to be different. And that is a problem. And this is, again, in the relationship, what I said at the very beginning, it's going to drive our costs up. And the higher those costs are going to be, the slower the introduction of photonic integrated circuits for space is going to be. So maybe we need to do something as a community about that.
I'm happy to help, because my job is to actually bring all of you together and make you talk to each other. You guys are a fantastic group. Any further question for Guillermo or for the rest? So for me, it has been a really good, really great meeting. There's so many room for collaboration here. I would like to ask my friend from Lumibird, what do you think about the meeting and what kind of follow-ups you want to do after this?
Sorry, can you repeat the question, please?
What do you think about this meeting and what kind of follow-up collaboration would you like to do after this? With which partners?
Yeah, this is my first participation with this list of meetings. So I have also another one in mind, the one for which was scheduled at the 8th of May. So most probably I will also attend this one. And I think that it's a good opportunity to meet the end users in order to understand what they are really need of. And I took some notes, and I will get back to some of the presenters that they presented today in order to see if we can help them as a Lumibird in their research and in their projects.
It was great to have you here because we need always to have the whole supply chain, and having the lasers from Lumibird, it's really great. The marriage of Cheopsis and Quantel is a marriage made in heaven. Jose, from iPRONICS, you gave us goosebumps to all of us with your dream, with your reality of having in 2 years an optical FPGA. Any closing remarks, any ideas, any room for collaboration? What did you think about this meeting? We have you muted. We need to have you unmuted so we can hear.
Okay.
Yes.
Right. Okay. So there are two things. First, from the pure microphotonics point of view, there is a lot of opportunity for photonics and especially for integrated photonics. So there is a very exciting path in many applications, and we have seen some of them here, but there are others. And then also from it's been quite a niche subject, and this may be the cause why there still need to have some kind of standardization, kind of let's say a more serious normalization towards commercial products that can be tested in different environments. But this will probably be developed in the following years. And of course, from my point of view, I think that it's being so a transversal technology, because RF photonics is more than the typical defense application, and people are starting to see that this is more and more. Everywhere you need to interface wireless and fiber, you're going to need to have microwave photonic inspired systems. So I hope that there's a chance for all of us and for many other players working in integrated optics, for example, not only in application specific, but also in programmable. Of course, I see a lot of opportunities there, and of course, what can I say? Yeah, it's very exciting. Yeah.
I have been listening to all of you. I have been taking notes as well. As you can see, these are my learnings from this meeting. I don't know. Can you see my screen? Yes, you can, right? So these are my learnings from this meeting. So for me, it is clear. The first question we wanted to answer is there a peak platform? And I think the presentations from Guillermo and from Martijn and from Michael were very clear. So there is a need for a hybrid platform that can actually combine the low losses of silicon nitride, the great job that LIGENTEC is doing, with the versatility of an indium phosphide platform. But we have a problem, two problems. The first one is the packaging that was very clearly specified by both Hakimeh and Kasia, and also the radiation tolerance. There is still the need of having a space qualification partners in the peak community for the indium phosphide. And in this, we are lucky to have CSEM. We need to have also Thales, Alenia. If you guys are listening, we need you here. We need to make sure that indium phosphide platform is space qualified. For me also, it was clear the work of Guillermo Carpintero is spectacular, but it is clear that we need to have a standard platform to have the co-package of indium phosphide with low noise tunable local oscillator, with microwave antenna. There's still some room to cover there. The technology is there. Guillermo has proved it's possible, but not as mature as it needs to be to satisfy the need of Kasia from AIRBUS. Also, there is a standard solution for beam steering. I think many people are really trying different things. Liones has done amazing things for beam steering. Guillermo has proved a lot as well. I know Michael is working with some partners on different beam steering applications. I know Martijn has also been looking at this. There is still the need to see what we need to do to satisfy the need of the end users, both on the datacom telecom, on the wireless broadband networks, as well as in the space. And finally, something that was in the beginning showed by Kasia, but we didn't talk too much about. There is the need of generation of higher frequency, the O band, the B band, the terahertz band. Guillermo is doing quite amazing things on the terahertz as well. I plan to have an event, an online technology meeting on terahertz to cover this. But this, in my opinion, has been the summary of an amazing, amazing afternoon. I would like to, first of all, tell you that I miss you, that I want this virus thing to be over as soon as possible so I can travel. The second thing, I want to ask you to stay home. Stay home. That's the best thing you can do for the community. Chat with me, call me. I'm always bored. I always happy to talk to you. Have a fantastic weekend. And until the next time, Jose and Ana, I'm really happy to have you as friends. See you later. Be epic. Bye-bye.
Bye-bye.
Bye.
Bye. Have a nice weekend.
Bye. Have a nice weekend. Bye-bye.
Have a nice weekend.